Good morning, dear students. I am Dr. Nagaraj, your physics professor, explaining VTU engineering physics for computer science, engineering and allied branch students. I have already uploaded videos on two modules. They are quantum computation and physics of animation. And there was a very good response from your side. I am really honored by your response. I am really happy with your positive feedback and comments. And it gives me immense strength to go ahead, to march forward in this journey. So many of you have requested me to do videos on other modules also. Yes, I will definitely fulfill your requirements and your request will be definitely met. I'm already doing numericals videos and I'm uploading numericals videos. I have uploaded numericals videos on quantum computation. Shortly I will upload other module numericals videos also, and meanwhile I will do even model paper discussion. So now today with this video I start another module, that is conduction of electrons in solids and then superconductivity. So in this video I start with superconductivity. Later on I will come back to classical theory and quantum free electron theory. Okay, superconductivity, under this title we have to discuss what is superconductivity, what are superconductors, example for superconductors, the concept of critical temperature, and then properties of superconductors, effect of magnetic field on the superconductor, Meissner effect, and then classification of superconductors, type 1 and type 2, concept of critical field, like that it goes. And also we have to discuss one theory called BCS theory, Cooper pair formation, and then Josephson effect, and there are two types in Josephson effect, DC effect and AC effect, and then squid and superconductor quantum interference device, and use of squid in the designing of qubit. Already you know what is qubit. So quantum computation totally depends upon superconductors, and the processors, microprocessors, are made up of superconductors, so we call them as superconducting processors. So superconductors are part and parcel of our quantum computers. Anyway, this is just outline. You can expect one full question including numericals from this particular chapter, that is from superconductor. Okay, let me give a brief history of superconductor. Way back in 1911, one physicist by name Kamerlingh Onnes was studying the effect of temperature on the resistivity of mercury. So you already know in PUC resistivity is directly proportional to temperature. As temperature increases, resistivity also increases. As temperature decreases, resistivity also decreases. Okay, so he was studying the effect of temperature on resistivity, and the graph was like this. So when he reduced the temperature, resistivity also started reducing like this, and he expected this type of curve. Okay, why this type of curve? That I will tell you after I finish off this particular discussion. So he expected this type of curve, but for his surprise there was a sudden fall in the resistivity to 0. So then onwards it was 0 only. This fall occurred at a temperature of 4.15 Kelvin. Remember, temperature is measured in Kelvin here. So Kamerlingh Onnes noticed that the resistivity of mercury reduced to 0 all of a sudden. It is not a gradual decrease, all of a sudden to 0 at a temperature of 4.15 Kelvin. Then onwards it continued to be as 0 only. Resistivity continued to be 0 only. That means mercury lost its resistance property at 4.15 Kelvin. We know if the resistance is very high, it is a bad conductor. If resistance is very low, then it is a good conductor. So resistivity is a deciding factor. So resistance is already known to you, resistivity is already known to you. Resistivity is nothing but resistance of a conductor whose length is 1 meter, cross sectional area is 1 meter square. So this you studied in PUC. So when resistance is more, we call it as a good insulator or a bad conductor. When resistance is less, it is a very good conductor, bad insulator. So resistance, resistivity, they are all deciding factors for the conducting nature. So more the resistivity, more insulating property, less conducting property, like that it goes. So when the resistivity increased, conductor became more and more good conductor. But when resistivity became zero, what to call it as? Shall we call it as a very good conductor, extremely good conductor? What type of adjective you want to put? No, there is no adjective for that. It is to be called as a superconductor. Okay, so it is not only a conductor, it is a superb conductor. So that is how the name came as superconductor. So superconductivity is a phenomena. Superconductor is a substance exhibiting this phenomena. So now comes the definition of superconductivity. Superconductivity is a phenomena in which resistivity of a material reduces to zero at a particular temperature. So it will lose all its resisting property. Then onwards it continues to be as a very good conductor. That is nothing but superconductor. So superconductivity is the zero resistance state of the substance. Rho equals zero. Okay. And the substance exhibiting this zero resistance state, zero resistivity state is called as a superconductor. So he noticed superconductivity in the case of mercury at 4.15 Kelvin. The temperature at which resistivity becomes zero is known as critical temperature, represented by Tc. So what is critical temperature? It is a temperature below which resistivity of the substance or the material or the element becomes zero, or it is the temperature above which resistivity is greater than zero, or it is the temperature at which a normal conductor converts, this is the conductor state, converts into superconductor state. So demarcation line it is. Critical temperature is a sort of demarcation line. So this was a very sensational discovery. Resistance becoming zero is a wonderful property, in fact, you know. Why it is so useful, we will discuss later on. So when Kamerlingh in 1s discovered this property in 1911, it was a very sensational discovery. So he showed the world that it is possible to make resistivity zero much earlier to 0 Kelvin. So in the case of mercury, it became zero at 4.15 Kelvin, called critical temperature. So critical temperature is the temperature at which resistance of the material becomes zero, resistivity becomes zero, and the material converts into superconductor. Okay. Well, after the discovery of superconductivity in mercury by Kamerlingh 1s, many other people started working on it, and they also came out with the same property in some other elements. So some people noticed superconductivity in zinc, aluminium, tungsten, okay, so lead, all these things they started exhibiting superconducting property. In fact, some people noticed superconducting property in aluminium at a critical temperature of 1.18 Kelvin. In the case of lead, critical temperature was around 7.5 Kelvin. That means lead started behaving like a superconductor below 7.5 Kelvin. Okay, at 7.5 Kelvin it lost all its resistance, all its resisting property, and converted into superconductor. So this is the beginning of superconductivity. When superconductors were discovered, okay, for many years critical temperature was very small only. See, you look at the values: 1.18 Kelvin, 7.5 Kelvin, 4.15 Kelvin, they are all very small. See, room temperature itself is 300 Kelvin. Remember, we are talking in terms of Kelvin, not in terms of Celsius. In Celsius, 27 degrees centigrade or 27 degrees Celsius is the room temperature. For that 27, you have to add 273, then it becomes Kelvin. Okay, from Kelvin to Celsius you have to subtract. Say for example, 7.5 Kelvin means minus 273, it is minus 273. So 5, okay, so 3, this becomes 2 minus 7 means 12 minus 7, 5, this is 6, this is 2 minus 265.5 degrees centigrade. It is too small, and it is of no use, in fact. Okay, we will discuss all these things later on. What I mean to say, superconductivity is a low temperature phenomena. When it was discovered, it was at very low temperature. Even today, we are not able to get a superconductor at room temperature. That means at 300 Kelvin or at 270 degrees centigrade, we have not achieved, but we are still optimistic. At day will come, our scientists will definitely find out a superconductor which will work at room temperature. If you get a superconductor at room temperature, things will become drastically, these things will change drastically, and there will be so many changes in our day-to-day life. So application part, I will explain the impact of superconductor on our day-to-day life later on. Back to superconductors. So I just mentioned what is Kemmerling's oneness experiment and what is this rho versus T, effect of temperature on resistivity. Dear students, I was talking about this line, dotted line. Let me come back to that line. Here I will explain the concept of Phonon as well as Mathesons rule. See, resistivity. First of all, what do you mean by resistivity? Resistivity is nothing but resistance due to unit conductor, unit dimension conductor. What is resistance? After all, resistance is nothing but opposition, and it arises due to collision between electrons and ions, or electrons and lattice points. See, inside the conductor we have atoms or ions sitting here and there, right? And electron is simply moving inside the conductor like this. It goes here, collides, comes here, goes here, like this, like this. So it is totally a zigzag motion. After each collision, electron will lose its memory, all the energy it will lose, and it will start the journey once again afresh. Okay. That means electron cannot move smoothly because of the opposition, because of the collision. So resistance is mainly because of collision. Collision irodinda namage opposition barta ide. So what is the cause for the resistance? It is collision. Now collisions are due to presence of lattice points inside the conductor. Suppose if you raise the temperature, then the lattice points will start oscillating. Then electron will suffer more and more collision. How it is, I tell you. See, you just picturize your classroom. You all are sitting and your teacher is walking in between the two rows of the desk. Okay, so when he is walking, he may not suffer any collision because that passage is free. Suppose while he is walking, you also get up, move out of the desk and start moving along with your teacher, or you are going along with the crowd in the market, there is every chance of collision, and the collision rate will be more. That means collision rate increases if atoms are also moving, ions are also moving. When the ions are moving, when the ions will move only when you increase the temperature. So when temperature increases, atoms starts moving. See, sometimes I call it as atoms, sometimes I call it as ions, sometimes I call it as lattice points. They all are same. For time being, let us take them as same only. So when our electron is moving, due to thermal vibration, see, there will be more and more collision. So as the temperature increases, resistance also increases. Conversely, when temperature decreases, resistance also decreases. Suppose if temperature becomes 0, resistance won't become 0. Why? Because inside the conductor we not only have pure ions, we also have some impurities sitting here. See, for example, you are talking about copper wire. Inside the copper there may be a trace of brass, or inside the gold there may be a trace of copper. So some impurities are sitting here and there. So those impurities also will contribute. See, dear students, collision is collision. Who is offering collision? That is secondary thing. First of all, is there any collision? Yes. Who is offering comes next. If the collision is offered by pure atoms or ions, then the resistivity is called as pure resistivity. If the resistivity is due to collision between electron and our impurity, definitely it is called impure resistivity. And that impure resistivity is dominant at very low temperature, and pure resistivity is dominant at higher temperature. So when you plot the resistivity versus temperature, at higher temperature it is almost linear increase. As temperature increases, resistance also increases. When you decrease the temperature, I expected this to become 0, that is for a pure conductor, but no conductor is 100% pure. There will be some impurity. Therefore, resistance won't become 0. It will exist little bit even at 0 Kelvin. This is called residual resistivity, also called as impure resistivity. So this is due to impurities contribution. This is due to pure atoms contribution, which I will write as pH. What is that pH? I tell you now, another 2-3 minutes. According to Matheissen, total resistivity is rho I plus rho pH. In PUC, you have derived the equation for rho or sigma. Sigma is equal to Ne square tau by m. Rho is just reciprocal, that is m divided by Ne square tau, where m is mass of the electron, n is number of electrons per unit volume, E is charge, tau is collision time, that is the time interval between two successive collisions. Okay, so whether you have pure atoms or impure atoms, mass of the electron remains the same, number of electrons remains same, charge on the electron remains same, only tau will change. Therefore, this becomes m divided by Ne square into 1 by tau I, that is the contribution from impurity, plus 1 by tau pH, this is the contribution from pure. This equation is known as Matheson's equation. You can expect this also. Discuss the effect of temperature on the resistivity and hence arrive at the Matheson's equation, or explain Matheson's rule. See, when I say rule, it need not be in the form of statement. Whole discussion can be taken as a rule. So according to Matheson, resistivity is due to collision between pure ions as well as impure ions. In the higher temperature range, pure ions contribution is more. In the lower temperature range, impure atoms contribution is more. A graph of rho versus T is as follows. The dotted line represents pure conductor. This real line represents a impure conductor. Okay, now coming back to this word pH. Dear students, what actually pH stands for? pH stands for phonon. Phonon is similar to photon. It is analogous to photon. What is photon? What is phonon? I will explain. Dear students, just wait. I have started with superconductor, but somewhere I went to the side of Phonon and then Matheson's rule. Actually, it is also part of the syllabus only. Don't think that it is beyond the syllabus. You may expect this question also. Write a note on Phonon concept and hence discuss Matheson's rule, or discuss the effect of temperature on resistivity, arrive at the Matheson's equation. Also write a short note on Phonon. This is also one of the question you can expect this for 6 to 8 marks, right? And moreover, we are going to use this Phonon concept in our superconductors. That is why I am introducing it now. We need this concept of phonon later on. Phonon andre eno. Just now I said it is analogous to photon. Photon andre eno nodi ನೀವು Einstein's theory na ಜ್ಞಾಪಿಸ್ಕೊಳ್ಳಿ. Photoelectric effect. Planck ಹೇಳ್ತಾನೆ energy is emitted in the form of a packet, discrete energy, but he never said energy is emitted in the form of particle. Planck never said this, but when Einstein modified it to explain photoelectric effect, he said each quantum of energy is associated with imaginary particle called photon. So photon concept was introduced by whom? By Einstein. So according to Einstein, photon is a particle associated with electromagnetic energy. That's all. That much is enough for us. And you know enough about photon. You studied all these things in PUC. Photoelectric effect chapter you already studied. So photon is an imaginary particle associated with electromagnetic energy. Okay na? Now coming to phonon. See dear students, we are talking about what is called metal or conductor. Inside we have atoms arranged in a particular manner. See, these atoms are arranged in a regular order. So like this, right? So we call these atoms as lattice points, right? So here to here, this is interatomic distance. Crystallography, please recall crystallography. This is nothing but a sort of mesh which I call as lattice plane. I can have lattice plane like this, I can have one more lattice plane like this, I can have one more like this, right? So or I can have even like this also, like this also. These are all lattice planes. In chemistry second PUC you might have studied body centered crystal, BCC, FCC, right? So each plane is nothing but a lattice plane. At each corner I have what is called lattice point, right? Depending on the position of the lattice point, I can classify it into body centered crystal, face centered crystal, simple cubic crystal, like that. So crystallography, that is not that much needed for me. I just need the concept of lattice plane. So dear students, this is one such lattice plane. Atoms are sitting at the corners. Now when you raise the temperature, right, this lattice plane will vibrate, or when electron comes and hits the atom, the lattice plane will vibrate. Like when you hit the board, or when you hit the membrane of the drum, or when you hit some wall, so there will be a small vibrations, right? So same, or if I hit the paper, say if I hit the paper, it is vibrating. So whenever it is vibrating, right, any vibrating body, right, will emit energy. Like my vocal cord is vibrating, it is emitting energy. What energy? Yes, it is sound energy. So like that, even this paper also will emit energy. But don't think that all vibrating bodies emit only sound energy. Sound energy is also one form of the energy. So here when I hit the paper, or when I hit the lattice plane, the lattice plane will vibrate and it starts emitting energy. Well, that energy is either in the form of heat or in the form of sound. Okay, well, now we have, similar to electromagnetic energy, thermal energy and sound energy. So like electromagnetic energy is having one imaginary particle photon, our thermal energy also should have imaginary particle, that is called phonon. Now you can say phonon is an imaginary quantized particle associated with lattice vibrations, associated with thermal energy due to lattice vibrations, associated with sound energy due to lattice vibrations. ಎಲ್ಲೆಲ್ಲಿ lattice vibrate ಆಗುತ್ತೋ, ಎಲ್ಲೆಲ್ಲಿ collision ಆಗುತ್ತೋ, ಅಲ್ಲೆಲ್ಲನೂ energy ಬರುತ್ತೆ. Okay, that energy will be having one imaginary particle called phonon. So phonon is similar to photon. Photon is for electromagnetic energy, phonon is for thermal energy and sound energy. Well, inside the conductor, phonon is responsible for transfer of the sound. So how fast the sound propagates, means the speed of sound. So sound energy propagation is done with the help of phonon. I tell you dear students, this is the first time you are coming across with the concept of phonon. You have not studied about phonon anywhere in your PUC. Photon you might have studied but not the phonon. So ಒಂದು ಕಂಡಕ್ಟರ್ ನ ಒಳಗಡೆ, ಒಂದು ಮೆಟಲ್ ಪೀಸಿನ ಒಳಗಡೆ ಸೌಂಡ್ ಪ್ರಾಪಗೇಟ್ ಆಗಬೇಕು ಅಂದ್ರೆ, in order to propagate the sound, there must be a particle that is called phonon, right? So phonon is responsible for transfer of sound energy. Not only that, when you heat the conductor, how much heat it will take or how much heat it will give, that is called thermal capacity. PUC you might have studied in thermodynamics, heat capacity or thermal capacity. How much heat it takes, how much heat it will give, that also decided by this particle called phonon. So phonon plays a lot of role, many roles inside the conductor. So in summary, in total I can say, inside the conductor we have mainly two movable particles. Two movable particles, they are electron is one movable particle, and phonon, that is another movable particle. Electron is a particle having mass, it is visible particle. Phonon is invisible particle, it is imaginary particle, do not have any mass. Electron is responsible for electrical conductivity, thermal conductivity, flow of heat, okay, flow of charge, like that. And phonon is responsible for flow of sound, absorption of heat. Phonon is similar to photon. Photon is for electromagnetic energy, phonon is for thermal energy and sound energy. It arises when there is collision and vibration. Okay, it is also quantized particle. Well, now coming back to this, rho pH. What is this pH now? it is phonon. Why you are writing pH? Because at higher temperature collisions are contributed by pure atoms, and pure atoms are dominant, therefore we have full of vibrations only, full of vibrations, therefore it is exchange of energy between electron and the pure atom in terms of phonon. That's why I am writing it as rho pH. Okay dear students, here I explained the effect of temperature on resistivity, right? Also effect of impurity on resistivity. In case of Kömmerling 1s experiment, he thought he will get the graph something like this, but for his surprise he got it like this. Why? We shall try to find the answer later on. It is not so simple to find the answer. What is superconductivity? Why superconductivity exhibited by some materials? What is the role of critical temperature? Why it is so small? So many questions. I tell you dear students, already about 3 to 4 Nobel Prizes are awarded for superconductivity work, but even today we don't have superconductivity at superconductor at room temperature, and more and above that we don't have a very satisfactory convincing theory which explains superconductivity, both low temperature superconductors and high temperature superconductors. Adನ್ನು explain ಮಾಡುವಂತ theory even today ಇನ್ನೂ ಸಿಕ್ಕಿಲ್ಲ. ಕೆಲವೊಂದು theories ಇದಾವೆ, but they are able to explain only up to certain extent. Okay, whatever we know that I will explain. I will come back to you in my next video about properties of superconductors, and then something about Matheissen effect, and then critical temperature, critical field relation. Well, I stop here. Please like my videos, share these videos. Okay, thank you very much.